Good morning, young people. This is Mr. Williams, and it is Tuesday, November the 5th, 2019. I'm going to be out of the classroom today, working on adult business at the district. No, today it'll be at the union office. And I don't want to get behind, so I'm going to do my normal lesson, and we're going to do this by video. I just realized I put down my reading glasses and I have no idea where I put them, so give me just a second. I have a hard time reading books, so let me find the reading glasses. You know what? I think I took them home with me, so no, here they are in my pocket. I tell you what, children, it's no joke getting older, and I'm not ready for it yet. It just happened. But there you go. So when we left off yesterday, we were talking about Newton's second law. So far we've learned about Newton's first law. Newton's first law says an object in motion will continue in straight line motion at a constant speed until or unless it's acted on by a net outside force, and an object at rest will remain at rest until or unless it is acted on by a net outside force. Newton's second law says that force is equal to mass times acceleration. So we explored that a little yesterday. Today we're going to talk a bit about Newton's third law. So before we do that, I want to be clear on what force and mass and net force means. We talked about it yesterday, but I just want to review briefly. Force, it's a push. My handwriting is terrible, but you knew that about me already. A push or a pull. It can be contact or non-contact. We're going to be dealing with contact forces only, up until I tell you otherwise. Non-contact forces are special cases. The non-contact forces we're going to deal with in this class, we're going to deal with gravity a little later, a couple weeks from now, and we'll deal with electricity in the spring semester. There are other non-contact forces, two other non-contact forces. We're not going to deal with them this year. If you take AV Physics 2, we will talk about magnetism and the nuclear force. So those are other non-contact forces. But there's only 4 non-contact forces, and we'll only talk about 2 of them this year. Other than that, everything else is going to be contact. So mostly it's going to be contact. A push or a pull where you make contact with another object. And force is measured in units of newtons. The symbol for a newton is a capital N, and 1 newton is equal to a kilogram times a meter per a second squared. You might ask where that came from. By Newton's second law, F is equal to ma. Mass is measured in kilograms, and A is measured in meters per second squared. So the units of mass times acceleration is kilograms meters per second squared. That's why force is measured in those units. Also, what is mass? Mass. It is how much stuff is inside an object. Mr. Williams, what is stuff? What a really good question. That's a hard question to answer. Quarks, leptons, protons, neutrons, electrons, all kinds of hadrons, stuff. That I said a bunch of words, most of which mean absolutely nothing. This is like I'm spouting gibberish. So the answer that I can give depends on what you already know. So let me say it this way, instead of spouting off a bunch of science-sounding words, which may or may not be true, but it certainly are meaningless to you. Let me just say that if you have a basketball that is filled up in the normal way, and then you take that basketball and you suck all the air out of it with an air pump and you fill it with water. In the first case, when it's filled with air in the normal way, there's less stuff inside the basketball. In the second way, when you fill the basketball with water, it has more stuff inside of it. Its volume doesn't change. The size of the basketball is the same in both cases, but the amount of stuff inside of the basketball can change. In the same way, if you have a solid brick of styrofoam, imagine it, a brick of styrofoam. Well, that's probably not going to, it's going to feel like there's not much in there. You go to shake it, and it's easy to shake because it has a lot of acceleration when you apply a force to it, like we talked about yesterday. On the other hand, if you took a brick of the same size, but instead of being made out of styrofoam, it was made out of iron, well, it would be a lot harder to give the iron brick the same acceleration that you give the styrofoam brick. You would have to apply much greater force to the iron brick to achieve the same acceleration that you have on a styrofoam brick for a far lower force. That is evidence for us that there is more stuff inside the iron object than there is inside the styrofoam one. This is because of Newton's second law. Whatever mass is, mass has an important role to play when determining how an object accelerates. That's the experimental way that we can figure out how much stuff is inside an object is we try to accelerate it. Try to jiggle it or shake it, or you hold something in your hand and you move it, you jiggle it, and then you can tell whether it's massive or not. So mass is how much stuff is inside of an object. Mass determines how resistant an object is to acceleration. All right, good. That's our review from yesterday. Let's go on to what's new today. What's new today is Newton's third law. For every force exerted there exists an equal force in the opposite direction. I should say equal magnitude, so I'm going to write the word magnitude. M-A-G-N-I-T-U-D-E. It's magnitude. For every force exerted, there exists an equal magnitude force in the opposite direction. So this may seem a little odd, so let's talk about it for a second. let's say that you're playing softball or t-ball. Let's say you're playing t-ball when you're a little kid. So you have the ball sitting on the tee. There's your ball sitting on the tee. And you swing your bat with a mighty thwack. Here comes the bat. When you strike the ball, here's a question to think about. When you strike the ball, does the ball hit the bat? Or does the bat hit the ball? Or do they both happen? Do they hit each other? So think about it. And then think about how hard they hit each other and how you know. Well, we know most people don't have any trouble saying the ball hits the bat. I mean, the bat hits the ball. But then the question is, does the ball also strike the bat? Well, imagine if instead of using the bat, what if you used your hand? What if you swung your hand really super duper hard? What would you feel in the palm of your hand? Wouldn't it feel like the ball had hit you? So your hand is a force sensor. Our bodies sense force. So if instead of using a bat, you used your hand, it would feel like the ball hit you, wouldn't it? Even though you hit the ball, you would also feel like the ball had hit you. Now, how hard did the ball hit you? Did it hit you as hard as you hit it? Did it hit you less hard than you hit it? Or more hard than you hit it? This is not an easy question to answer. And it's a little confusing because the ball responds wildly to the bat. If you strike the ball with the bat, the ball goes whoosh and it flies off. Woo! It goes really, really far and fast. With the bat, it doesn't go flying off in the backwards direction really far and fast. Hold on just one second, kids.
Oh.
So then the question becomes, why doesn't my hand, or why doesn't the bat respond to the ball the same way that the ball responds to the bat? If, like Mr. Williams just told you, that the force of the ball on the bat is the same as the bat on the ball, then why don't they respond the same to each other? That's a really tricky question. To answer that question, you have to go back up to Newton's second law. So Newton's second law says that if you have a force that's identical on two objects, but one object is more massive, then what has to happen to that more massive object's acceleration to compensate? Well, its acceleration would be smaller. So let's think about this. Which has more stuff in it, the bat or the ball? Well, that's pretty obvious. See, the bat has a lot more mass in it, and the ball has a lot less. So if Newton's third law is true, and there's the same force that the bat exerts on the ball as the ball exerts on the bat, well then, what effect would be had on the bat? Well, its mass is really big, so its acceleration or change in velocity would be very small. So if the bat was swinging along at 20 meters per second and it strikes the ball, well, its mass is large, so its change in velocity would be small. It would slow down slightly. Think about it. If you've ever hit a ball with the bat, does the bat slow down when you strike the ball? Well, yes, it does. Does it slow down a lot? Well, not a whole lot. If you've ever had a coach, they probably told you to swing through the ball. Swing through the ball so you maximize your swinging power. We're going to talk more about why they say that later. But for now, what I'm trying to emphasize to you is the bat slows down. Not a lot, but a little. Now let's think about the ball. If it gets the same force on it that the bat got on it, but its mass is much smaller, then what has to happen to its acceleration? Well, if its mass is small, its acceleration has to be super duper fast, super duper big. So then its initial velocity is 0. It's just sitting there minding its own business, and it gets hit by a bat. Bam! Then what has to happen to its acceleration? Its acceleration has to be really, really large if it has the exact same force on it that the bat has on it. So let's go back to our original problem with this situation. If the same force strikes the bat as strikes the ball, why are there such different effects on the bat and the ball? I think now we have an answer. They can have the same force on them, but the difference is that the ball's mass is so tiny that it experiences a much larger acceleration for the same force. And the bat's mass is so large that it experiences a much smaller acceleration for the same force. When I return tomorrow, I'm going to show you a video of two young people holding scales facing each other. So these are bathroom scales like your grandma might have in her bathroom. These are not digital scales. These are going to be old-fashioned scales like I used when I was a little boy. So you may not have seen very many of them unless you go visit your grandparents' house or something. Or maybe your parents have an old one at their house. I don't know. So there'll be two bathroom scales. They look like this. And there will be two kids that are pushing on them. No, that's a kid's hand. It doesn't look very much like a hand. But you know I can't draw. So here's another kid's hand. Whatever. So two kids pushing the bathroom scales towards each other. I want you to think about what the scales read. So if you ever pushed on a bathroom scale, you know it'll tell you like 10 pounds or 60 pounds, or if you stand on it, it might not be 100 pounds or however much you weigh. So if this kid is pushing this way and the other kid is pushing that way, and the scales don't move, would these two scales read the same or would they read different? So that's a question I'm going to leave with you, and you should be able to answer it now. But we're going to think about it more, and we're going to talk about it more tomorrow. I'm going to show you a video. Okay, I think it's time for us to start to put all this together, besides which I'm going to have to leave pretty soon. So I'm going to give you a couple questions to work on. Your sub is going to turn off the video, and then you guys are going to work together in groups, just like always. And when I return tomorrow, we'll go over some of these questions together. So you should be on page 122. And I want you to work for the rest of class today on numbers 39 to 41. And that will be due on Wednesday when I come in. So you need to be ready to answer the question as soon as class starts tomorrow, because I don't want to waste any time. All right, if you have any questions or concerns, you can email me like always. Thank you. Be good.